Hello. Now we're going to continue our work with quadratics, and we're going to look at the maximum value, so the maximum y output of a quadratic, or the minimum y value, the smallest y value that we could get out of a quadratic. And to do that, we're going to use completing the square. So to begin with, we're going to have a quick reviser of perfect squares and then look at completing the square and how we can use it to find the maximum or minimum y output. Now, on perfect squares, any number that can be written as something squared is called a perfect square, or a whole number squared if we're dealing with pure numbers. So 4 is a perfect square because it can be written as 2 squared. 16 is a perfect square because it can be written as 4 squared, or 25 is a perfect square because it can be written as 5 squared. So x multiplied by x would be a perfect square because it can be written as x squared. So x plus 5 is a perfect square. It's something squared. If we multiply it out into a normal quadratic type situation, we would end up with square the first by the second, and double it. So first by the second, 5 by x is 5x, and double it is 10x, times square the second is 25. 5 squared is 25. If I follow the pattern for my next example, I'd have square the first by the second, and double it. So I'd have minus 3x, and double it would be minus 6x. Square the second would be plus 9. Now let's have a pause for a moment and look at our pattern. If I have the number in my bracket in the second term in my bracket here, and I look at the number that is the coefficient of the x value, if I half the coefficient of the x value, so 10 over 2 is equal to 5, 10 over plus 10 over 2 is equal to 5. That gives me my number in my bracket, and if I square that, 5 squared, I get the number on the end of my perfect square. Likewise, if I have my minus 6 is my coefficient here, and I half it, minus 3 over 2, sorry, minus 6 over 2 I should say, is minus 3. And if I square that, minus 3 squared is 9. So for a perfect square, a pattern that we have to be very good at recognizing is that if we have the number in front of the x, half the coefficient of the x, and square the result, we get the number on the end of our perfect square. That is a key part of being able to identify perfect squares. We have to be able to recognize that this is a perfect square that we could square out. We have to be able to recognize that if we see something like that, we have to be able to spot that we could form a perfect square from it. So let's apply our pattern here to factorizing this next quadratic. So I have x squared minus 12x plus 36. So if I half the number in front of my x, I'd have minus 12 all over 2 would be equal to minus 6. And if I squared that, minus 6 squared, I'd get 36. That tells me, without any further work, that I can write down this is x minus 6 to be squared. Now there's a reason I'm very careful with writing down my minus 5 and my plus 10 and my minus 12 here, because it's important that we wouldn't have accidentally written this down as x plus 6 all to be squared. So be careful that you're keeping track of the sign of the number in front of your x when you are using this pattern. Let's try this one here. We have x squared plus 8x plus 16. What am I going to do here? I'm going to have the number in front of my x, so it's going to be 8 all over 2. So plus 8 all over 2 is going to give me plus 4. And if I square that, 4 squared, I get my 16. So that tells me, without any further work in factorization, that this is x plus 4 to be squared. Now, why do we care about this in terms of max and min? It's because of a particular thing that we know about squaring numbers. So to talk about that, I'm going to look at, or we're going to look at our two examples here where we have x minus 3 to be squared. If I look at the sketch I've drawn here of x minus 3 to be squared, if I solved this, hopefully we would all be happy that if we're going to get x minus 3 is equal to 0, x minus 3 would be equal to 0. If we were factorizing and solving it, we'd end up with x is equal to 3 is our only solution, so we get a repeated root. Now, if I look at my graph, if I have my repeated root here, what does it tell me about my smallest possible y value? Well, the smallest possible y output from my curve here is going to be y is equal to 0, and that's going to happen when x is equal to 3. So my minimum value is going to be at x is 3, y is 0. Now I can know that without drawing a picture because of what I know about squaring a number. If I had something like minus 10 to be squared, it would give me a positive number. It would give me 100. If I have 0 squared, it's going to give me 0. If I have 5 squared, it's going to give me 25, another positive number. So what can I say in general about something squared? Any number squared, so I'll write it down as x minus 3, but it could be anything inside this quadratic, must be greater than or equal to 0. There's no way for me to get anything smaller than 0 from this function. So the smallest value of y that I could possibly get from something squared would be 0. For any other value of x, I'm going to end up with something that's bigger than 0. If x is equal to 3, I end up with 0 for my equation. And for any other value of x, because I'm squaring whatever number is inside the brackets, I must get something bigger than 0. So if I can write something as a perfect square, if I can write the variable as a perfect square, I know that the smallest value that can come out of that is going to be 0. And I'm going to use that fact to find to figure out my maximum and minimum. Now, likewise, if I had minus a perfect square, what does that tell me? Well, it means that the thing that's coming out of my bracket, out of my square, must be positive. If I multiply it by minus something, that means it's always going to be negative. So if I have minus a perfect square, that tells me that automatically the biggest value that I can have out of this, so minus 3x squared, must be less than or equal to 0. If x was equal to 3, I get 0. And if x is anything other than 3, I'm going to end up with something positive coming out of here that then gets multiplied by a minus. So it's going to be smaller than 0. It's going to be a negative number. So that is my reason for wanting to complete the square for finding the max and min. Because if I can get the variables, if I can get the x stuff in my equation into a perfect square, then I know that its maximum or minimum value for the varying part is going to be 0. So let's put this into practice. If I have x squared plus 4x plus 6 is equal to 0. Right away, I see that I don't have a perfect square, because for a perfect square, what would I end up with? I would have plus 4 divided by 2, and then I would want a number on the end that is going to equal 2, and I would want 2 squared on the end. And I don't have that. I have plus 6 instead of plus 2 squared, which would be 4. So what I want to do is form a perfect square. So I want to end up with x squared plus 4x plus 2 squared. But I can't just randomly add in 2 squared into my equation, because that would change the equation. So if I'm going to add in plus 2 squared, at the same instant, I have to add in minus 2 squared. And because the sum of these two things is 0, this stuff just equals 0, I haven't changed my equation. I've just changed the way it looks, but I haven't fundamentally changed it. So now this part of my equation looks like a perfect square. It can be written as x plus 2 all squared. And I'm just left with on the outside minus 4 plus 6 is equal to 0. So I have x squared, x plus 2 to be squared plus 2 is equal to 0. Now, how does this help me? Well, it helps me because I know that the smallest value that this equation can have, the smallest y value that this equation can have, would be when when the stuff in brackets here is going to be 0. So what I want to do to find the minimum, in this case, because this is a positive squared bracket, I don't have a minus out here, so the minimum is going to be when x plus 2 is equal to 0, and that's going to be when x is minus 2. So I know that the minimum is going to be when x is minus 2. What is the y value going to be when that happens? Well, if I sub that in, I'd have minus 2 plus 2 to be squared, plus 2 is equal to 0, or is equal to y, I should say. So I'd end up with 0 squared plus 2 is equal to y is equal to 2. So the location of my minimum is going to be at x is minus 2, y is 2. Let's check that now. The brightness of our screen is going to change now. If I graph my quadratic that I was just dealing with on GeoGebra, what I end up with is my blue quadratic here, and I can see that the smallest y value that I could get out would be at x is minus 2, y is 2, which is what I found by completing my square. Brightness of the screen is going to change back now. So that is my using completing the square, and then I can use this where the quadratic part, where the squared part is equal to 0, is going to be the smallest output, because I would have y is equal to 0 plus 2 would be the smallest possible output. If I had any other value of x, if x was equal to 1, for instance, I'd have 1 plus 2 to be squared, and that would leave me with 9 plus 2 for my value of y. So for any other value of x, I'm going to be adding on something to my 2. So that's how I can use this to reason out where my minimum value must be.